So we can take that knowledge and utilize it to our advantage by talking about photoelectron spectroscopy. And this is a fancy technique that is able to utilize this idea that energy from electrons that are emitted through our photoelectric effect, they provide insight into the electron configuration of our sample. So if you recall from the first slide, if we shine a certain color light with a high enough frequency, electrons are going to be ejected. If we eject all of the electrons in some sort of atom, each of those types of electrons are going to have different energies associated with them based off of where those electrons are in the atom. So the data that we're going to get is related to that binding energy that I just described, which is the energy required to eject the electron. If the energy that's binding the electron in the atom, I need to put in that same amount of energy in order for it to be ejected. And the reason that is because energy is quantized. For example, if we had a binding energy of 0 kilojoules per mole, that would technically be a free electron, which we would never see in our natural worlds because we just don't have electrons flying around. And in general, higher energies correspond to electrons closer to the nucleus. In this respect, when we think about this, because the attractive forces are stronger, the binding energies of our electrons closer to the nucleus are larger. The y-axis shows our relative intensity, which is going to be related to the number of electrons that are ejected. And what we're going to be able to do is do some comparing to help us assess what orbital those electrons came from. So to talk through an example, here's the lithium photoelectron spectrum. Spectrum is a fancy word for a graph. So our x-axis is our binding energy and our y-axis is the relative number of electrons. And the key thing here is that we see 3 key pieces of information. The peak closest to the origin being here, is going to be the highest binding energy. So this peak here, we notice there's 2 peaks. Our peak to the left is going to have a higher binding energy. I'm going to abbreviate binding energy as BE, just to conserve some space. And further away, we have a lower binding energy. And what that indicates to us is that the electrons that are associated with this peak right here came from an orbital closer to the nucleus. So each peak is associated with a group of electrons in one specific orbital. So, for example, we have 2 different peaks here. This first peak and this second peak, each represent electrons from 2 different orbitals. So the electrons present here are from 2 different orbitals. Lastly, what our relative intensity shows us is that the height of the peak is associated with how many electrons are present. So if we move over to the y-axis, this is a height of 2. And if we move over to the y-axis, this is a height of 1. So what we've just determined is that because we understand electron configurations now, we know that the orbital that's closest to the nucleus is the 1s orbital. And the height tells me that our first peak on the left represents our 1s2 orbital. 2 electrons were ejected from our 1s orbital, and we can identify that because that peak is the closest to the origin, meaning it's our highest binding energy. Next, what we would be able to say is our second peak is representative of our 2s orbital. it has a height of 1. So this is representative of our 2s1 orbital, where 1 electron is in our 2s. And because you all know how to do electron configurations now, we can verify that the actual electron configuration of lithium is 1s2, 2s1. So what we've just seen in action in this figure, in this spectrum, we're able to verify that lithium's electron configuration is 1s2, 2s1. We're going to talk through one more sample and then a comparison as well. Our example number 2 is our photoelectron spectrum of oxygen. We notice that there's 3 different peaks here, which means there's going to be 3 different orbitals that are present in our atom of oxygen that has electrons in them. This electron has the highest binding energy, just to review, and this peak has the lowest binding energy. Now we go ahead and confirm our heights. This line represents a height of 1. This is 2. This is 3. This is 4. This is 5, and so on and so on. If we take a peek, we can first identify what orbitals these are representative of. The orbital closest to the origin is going to be our 1s orbital. The next lowest, or the next highest binding energy is going to be our 2s. And the next highest is going to be our 2p. And now, based off of the height, we can go ahead and identify how many electrons are in each of these peaks, or represented in these peaks. This has a height of 2, so this is 1s2. This is also a height of 2, so this is 2s2. And then this is going to be a height of 4, so this is 2p4. And we can verify that the electron configuration of oxygen is in fact 1s2, 2s2, 2p4. So what we were able to do is put enough energy into oxygen for all 8 of its electrons to be ejected. The first 2 have the same binding energy because they come from the same orbital. The next 2 have a lower binding energy, but because both of those electrons come from the same orbital, they have the same energy. And last but not least, the last 4 electrons come from the lowest binding energy orbital. And those 4 electrons all have the same energy because they come from the same orbital. Lastly, if we want to compare photoelectron spectra, we can go ahead, and the key thing here is identifying that lithium and beryllium have similar electron configurations. This is 1s2, 2s1. Beryllium is 1. This is 1s2, 2s2. So the key difference here is we can identify that this is beryllium because there are 2 electrons in our 2s orbital, as opposed to our lithium, where it's going to be 2s1 represented here. And when we talk about periodic table trends, I will talk a little bit about why this binding energy is shifted. So stay tuned for that. But our key here in our comparison is really identifying the difference in our heights, because lithiums looks different than beryllium because they have different numbers of electrons, and that will be reflected in the height representative of the relative number of electrons. So that's it for this lecture video. Go ahead and now work on our homework activity that's assigned, and I will see you in the next class. Bye, everyone.